Assalamualaikum everyone. So today we're gonna move forward to the Ansys simulation. So up to now you have solved some differential equations with MATLAB with the applied boundary conditions. But now we're gonna see that how can we import a geometry in Ansys and apply boundary conditions and have the simulation performed on Ansys. So the simulation that we're gonna perform today is actually the simulation of a signpost. Okay. So this is a signpost, and actually you have seen this kind of things in roads, like in the roads where different kind of lights are shown, like the red lights, yellow lights, and green lights are shown. So that portion is called the sign. Okay, so this is actually the sign, and at which this post is attached is called the post. Okay, and this is an assembled geometry. That means the top portion will have a different material made of, and the bottom portion will have a different material made of. The top portion is made of is given in our activity sheet. This is the aluminium 60626, and the bottom portion, that means the post, is made of steel, is given that. And different kind of boundary condition, that means the forces, you see different forces have been shown here and that are working at different sections, like here the downward force FZ1, and at the top there is WZ1, and a varying load is given. Okay, so before all that, to perform this simulation, you have to have Ansys installed in your laptop or PC. So a request to all of you to install Ansys. You can use any version, it's up to you, but I'm using Ansys 2020 because my laptop is a bit old. It cannot handle 2024 that much well. So it does not matter if you want to use 2024, 2023, it's up to you. You can use any version that you want. So as you know, you have installed, let's assume that you have installed Ansys in your laptop or PC. So for that, after the completion of the installation, you have to go to the search and you have to search for the workbench. Okay, so workbench, you have to open this one. Okay, I have already opened the workbench. So this is how it looks like. Okay, so you have different sections, different field you're going to perform. Like there is for the fluid flow, you have the Ansys CFX fluent, and for ICNG you have fluent, and for the turbo machine we have fluid flow. So there are different sections you can perform the simulation on. But as this is, if you go back to our activity sheet, so this is a structural analysis. So we're going to perform the structural analysis on this signpost to get the value of the stresses, the strain, deformation, and all that. So this is a structural analysis. So we have to go to the Ansys structural. If you look here, you'll find the static structural. Okay, you have to double click to open that. Okay, so this is how it looks like. So now you have to import the geometry, and as I said that this simulation, is more over concentrated on how to perform the simulation, not on how to design it. Okay, so that's why all the geometries that we're going to perform the simulation on will be given in your Google Classroom. So from that you download and import the file. And if you want to design a certain geometry in SolidWorks, so you can export that file into STL format, and you can import that here as well. So the geometry file that will be working today is given in your Google Classroom. You can download it from there. And now if you click on the geometry and right click, so you're gonna get the import geometry. Okay, so from here you're gonna import the geometry. Okay, so this is our geometry, so import that. And before that, as I said, we have to specify the materials. And this is an assembled part. There are two sections. The first portion is made of aluminium and the second portion is made of steel. So you have to specify these two materials. So for that you have to go to the engineering data. Okay, in the engineering data, so the structural steel is already predetermined, so you do not have to do anything with that. You have to add a new material that is called the aluminium 6061. Okay, aluminium 6061. Okay, so now if I add that, you see there's a question mark because I haven't specified anything. So the properties of the aluminum have been given in your lab manual as well. So if you look on here, the Poisson's ratio, sorry, no, the Young's modulus. The Young's modulus is given 1 e to the power 7 psi, and the Poisson ratio is given 0.33. So we have to specify these two things. Okay, if you go here, aluminum. Okay, so you see here the different properties you can find. Okay, so at the physical properties, the linear elastic. So if you go into the physical properties, you'll find the density and all other things. Okay, and if I go into the linear elastic, okay, and go to the isotropic elasticity, you're going to find these two things, the Young's modulus and Poisson ratio. Okay, before you input the value, make sure that you have the right unit. Okay, here the unit is in the psi, so we have to change the unit to psi. Okay, so psi, it is 1 e to the power 7, so 1 e to the power 7. Okay, and the Poisson ratio is 0.33. It's dimensionless, so it doesn't have any dimension. Okay, so it's done. Okay, and another thing is given, and that is in your lab manual, that is the density, and it is in pound per inch cube. Okay, so you have to have, okay, so this aluminum and the density, you see in the physical properties, in the density you'll find the density. If you click on it, the density you have to specify, it's not in kg per meter cube, it's pound per inch cube, this one. Okay, and it is, what is the value? The value is 0.0975. Okay, so you have to specify the value 0.0975. Okay, so now we have added a new material. So if you want to work with different materials and that is not specified in the Ansys, you have to create a new material, and you have to specify this kind of values, like the Young's modulus, the Poisson ratio, the density. And if you give those values, then it will have a new material, and you can work with that material. Okay, so now it's done. Now we can close this tab. Okay, now if I go into the geometry, okay, now sorry, we go to the geometry has been imported. Now we'll go to the model, so it will open the Ansys mechanical. Okay, so it will take some time. Okay, as long as it opens, now let's go to our lab manual. Okay, let me tell about these forces. Okay, so the WZ1 is actually basically the weight of the sign. Okay, but it is actually given on the top, because in the Ansys you cannot have the centroid predetermined. Okay, so if you want to determine the centroid, you have to have predetermined from your like the drawing, the 3D drawing, like the SolidWorks or anything you use. Okay, so you have to predetermine the centroid, because Ansys cannot automatically determine the centroid, so it cannot apply the weight at the centroid of the sign. That's why it's been given at the top. There will be some error due to that, but we're not considering that. Okay, and also you see the weight of this post is given here, the downward section. It is also the weight, but it is supposed to work at the centroid of the post. But as I mentioned, that Ansys cannot determine the centroid automatically. So if you want to determine the force at the centroid, then you have to have predetermined from your 3D drawing. Okay, so that's all. Now I think the Ansys mechanical is open. So this is your geometry. Okay, so if I look on the geometry, so this is the sign, and this is your post. So if I select here in the geometry section, you'll have, this is the post. Okay, and this section is our sign. And if you look on here, there's a question mark here, which is this one. Okay, why we have this one? This is the phantom surface, we're going to call, because if you want to apply certain forces, you see a varying load has been applied on the left of the post and the sign. So to apply this force, you have to have a surface or a face to be predetermined in your Ansys. So if you do not determine the surface, you cannot apply this first, because the sine is a curve, you cannot directly apply the force. So you have to have a certain surface predetermined in Ansys, so that then you can apply the forces. So to apply this force, we have to determine a phantom surface, which is this one. If you zoom in, which is this one, but it is showing an error because I haven't determined the thickness of it. So the thickness is also given in your lab manual. If I go here, where is it given? Okay, this one. Okay, 1 e to the power minus 3. The thickness is in inch, so I have to give the thickness. Okay, 1 e to the power minus 3. Okay, so now you see there's a tick mark, so it's been well defined now. So now I have to specify the material. As I said, that the post is made of steel. So we will select the post, and the post material is given as structural steel. It's already given. And if you select the sign material, we have to define as aluminium 6061, but it's given as structural steel. So let's change that. So if I change the material to aluminium 6061, okay, it's done. So now if you go into the mesh, okay, now before the mesh we have to determine the connections. The connection means, you see, this is an assembled part, so this is another section, this is another section. So the sign will have a kind of connection with the post, and there is a phantom surface. The phantom surface will have connection with the post, and the phantom surface will have a connection here with the sign. So we have 3 connections, so we have to determine the connections. Okay, so the connection and then contact, if you expand it, there are 3 connections, it's predetermined. So you see there's one connection between the sign and the post. You see, if you zoom in here, the red one here and the blue one. So here we'll have one connection, and this is the connection between the sign and post. So I want to rename that so that I understand it better. So it would be between the sign and post. Okay, that's done. The second contact region is, you see, this is between the phantom surface and the post. So it is between the, we have to rename that, between the phantom and post. Okay, and the third one is between the phantom surface and the sign. Okay, so it is between the phantom and sign. Okay, the most important part is actually what kind of the type of the connection it will have. If you look on here, the type, it is given as bonded. Bonded means it's fixed. It will not have any relative motion between these two surfaces. That means the sign and the post, it will not have any relative motion to each other. That means it is either welded or bolted. Okay, so this is called the bonded. And no separation means that if I give no separation, that means it will have a relative motion, but it will still attached to each other. That means it will have a relative motion to each other, but it is attached with each other as well. Okay, and there is another one, the frictionless. That means it will have relative motion with each other, but it will have no friction. And rough, that means it will have friction and all that. So we are considering the type as bonded. That means it will have no relative motion to each other. It is either it's a fixed and it is either bolted or welded. Okay, so it is also okay, and it is also bonded. Okay, so it's done. Now we will go to the mesh. So mesh, I think you know that we divide the section. Actually, in the math lab, you see that we have divide the like the length into the nodes, and also the we have taken the square matrix and divided into some sections. So this is basically that we're going to divide this whole geometry into small sections, and onto that we're going to perform the analysis. We're going to apply our differential equations and perform with the boundary conditions, and we're going to solve it. So we have to discretize this geometry into some sections. So for that we have to use the mesh. So there in the mesh, if you right click and insert, you see there's the method and sizing. So this is the most important parts. So first let's go to the method. So this is one method and insert one sizing. So the method is for, I'm going to select, you have to first select the geometry. So you see at the graphic toolbar, this is called the graphic toolbar, you see different selection options. Here we can select the vertex, that means a single point, and here if you select that, this will select an edge, and this will select an surface, that means a face. This is called the face selection. Okay, the face selection, and this is the whole body. So now we have to use a whole body selection because we're going to define a geometry to the meshing. So the method, for the method I have to define the geometry. I'm select the sign and apply. Okay, so the geometry has been selected, and under the method we have some methods to perform, like either it will be a tetrahedron and hex dominant and so on. So tetrahedrons means it will have four. I think you have an idea how the tetrahedron looks like, and the hex dominant is basically looks like a pyramid. Okay, so the hex dominant is better compared to the tetrahedron. So it's up to you. You can use any of that, and we're gonna use the hex dominant. Okay, so I think in the lab manual, is it determined that which method you're gonna use? Let me see. Let me see that. Is it predetermined? No, I think they have used the default one. Okay, so for the experiment purpose, we're gonna use the default one. Okay, but you can change it. Okay, you can change it. You can change it to hex dominant or anything, the tetrahedron. But hex dominant is the better. But we're gonna stick to the automatic. Okay. And okay, another section, if I would have used the tetrahedron, okay, there is a element order. Okay, so you can use the linear and quadratic. So as the name suggests, the quadratic is going to give you a better solution compared to the linear approximation. So you can also change that. So but for now we're going to stick to the automatic. Okay, automatic. So this is actually the method. I'm going to rename that. This is for the sign method. Okay, sign method. Sorry, it should be sign method. Okay, and then the sign sizing. If I rename that, sign sizing. So for the sizing as well, you have to also select the geometry. So I'm going to select the body selection, and here apply. So the geometry has been selected, and this is called the element size. So that means the lower the element size, the better the finer the mesh is. Okay, so I'm going to use the default. You can use it any number, like it's up to you. You can use 2, 3 inch or up to you. The less this element size, the better, the finer the mesh is actually. So I'm going to stick to the default option. Okay, so now I have another section that's called the post. So for that I have to use insert method, and this is for post. Okay, post method and we have to use another insert for the sizing. Okay, so and this is, if I want to rename that, it would be post sizing. Okay, so now let's go to the post method. You have to select the geometry, this one, and selection. And I'm also sticking to the automatic option, and you can also change that, up to you. The hex dominant, tetrahedron is up to you. So let's for now stick to the automatic. Okay, and for the sizing you have to select the geometry as well, this one, and apply the element size. The less the element size, the finer the mesh is. So if you want to increase the element size, then the computational power you need is higher, so it will need more time to solve. Okay, so it's up to you. Okay, so it has some kind of pros and cons. So if you decrease the element size, it will take more computational power to perform the solution. And if you have you know, 7, 10 or something, the higher, then it will take less time to solve. So it's up to you. Okay, so now it's actually even. So now if I want to go to here and generate mesh, see, it has divided this sign into some small sections, and also the post into some sections. Okay, so this is called the meshing. We have divided the whole geometry into small sections on where we perform the analysis. Okay, and if you look on the if you go on the mesh and static this, you see we have 4,219 elements. So the total element in the whole geometry is 4,219, and the nodes we have is 8,235. Okay, so in the MATLAB we have solved for only 5 nodes, 6 nodes, 50 nodes. You see that when we are dealing with the complicated geometry, we have a lot higher, actually a lot of nodes actually. Okay, now we have to apply the boundary conditions. Okay, so how many boundary conditions we have? If I go here, so first of all we have a force that is working on the top. That is actually basically the weight of the sign, but I mentioned that why it's given on the top rather than the centroid, because Ansys cannot predetermine the centroid. If you want to apply a certain force at a centroid, then you have to actually predefine it in your geometry. That means in your SolidWorks. Okay, so the first force is actually the top force, that is WZ1. The value of WZ1 is given as 14,000 pound. Okay, so now if I go here, okay, Ansys mechanical. So now the static structural. Okay, so here you have to apply the boundary conditions. Now if you right click here, insert. Okay, so first of all let's go here, let's see what we have. We have a fixed support at the end. Okay, so at the bottom end we have a fixed support, so we have to define this boundary condition. So for that you go to the structural, static structural, and insert, and there's a fixed support. You'll find this one, and at the bottom end, so you have to select, this is the selection options, we have to select a face or a surface at the bottom. So we have to select the face selection. Okay, and this one, the geometry, and apply. Okay, so this is the fixed support. Okay, now what we have at the bottom, we have a WZ1. so let's insert force, and the surface would be on the top, apply. Okay, so if you look on the lab manual, you see this is WZ1. The value of WZ1 is 14,000, and it is working downward. Okay, it is working downward. So if I go here, see the jet direction is upward positive and downward negative. So to have this actually on the downward sections, we have to use the negative sign. Okay, negative 14,000 is given, if I'm not wrong. Yeah, 14,000. So it would be negative. Oh, you have to use a vector. Okay, vector components, because it is only working on the z direction. Okay, so you have to use the components, and it's only in the z direction. So but it is downward, upward is positive, downward is negative, so you have to use negative 14,000 pound. Okay, see, if you look here, this is the downward force working here on the top. One important point, that when you apply these forces, you make sure that change the units according to your requirement. All our forces are given in pound. Okay, so we have selected the unit as this one. Okay, inch, pound. Okay, force, and so on. Okay, so make sure that if you're working with the meter, then you have to use this one, centimeter this one, millimeter this one. So make sure that whatever is given in your geometry, according to that you change the dimensions, the unit. Okay, so one force is given, actually been applied. Now if I look on here, we have another force that is working downward at this section, that is the weight of the post. Okay, so if I rename that, okay, this is actually the sine weight. Okay, sine weight. Okay, now we have to apply another force. Okay, so insert force, but that would be working here, but it's difficult to determine the surface. Okay, so for that, what we can do, we can go to the sine and right click and hide the body. Oh, sorry, not the sine one. Okay, show body. If you go to the sine, okay, not the post one, sine. If you want to hide the body, see, it's been hide. Now it is easier to actually apply the force. Okay, so now it would be this surface. So if I go here now, force, and set the face selection and select this surface. Okay, and it's also working downward, so that means we have to use vector components, and on the z direction, and the value is given fy1, sorry, not f1, fz1. Fz1 is given as okay, sorry, it is the density is given, the weight density is given. Okay, so that means the weight of the sine. So if you actually want to apply the weight at this point, that means we have predetermined it's a steel, and the geometry, in the geometry it has the dimensions, like all the dimensions it needs, and Ansys automatically calculate the volume and the mass, because it has the dimensions, all the dimensions, so that it can easily calculate the V, that means the volume, and we have determined the rho, that means the density, so it can easily determine the mass. That means mass is what, rho V, so rho times V. So if you go on the post, okay, and if you go on the properties, see, the mass is already been calculated, and also the volume, because the volume, the dimensions are given, so it can automatically calculate the volume, and also the the density is determined, so from that you can calculate the mass. So we have to take that, copy, and Ctrl C, and go to this first section, and at here we have to have a negative sign because it's working downward. Okay, you see, it's working downward here. Now I have to show the sign and go here, show body, it's working. Okay, so we have two forces been determined. One is the bottom, and here the sign, sorry, the weight of the post. Okay, now we have a varying load. Okay, before varying load, we have another load, that is Fy1, that is working here. Okay, so this all the forces are given considering the realistic scenario. That means, when the sign post is actually on the roads, it will face some kind of the wind, okay, or any birds will actually sit on the top of the sign. So it will have some weight, and also due to the wind, maybe the wind is coming from this direction or maybe from this direction. So this all the boundary conditions are given here, considering the realistic scenario. Okay, so we have also a force, that is Fy1. Value of the Fy1 is given is 8,000 lbf. So if I go here, okay, so it has to be applied here. So yeah, this is the, let's rename that with the post weight. Okay, now we have another force. Okay, we have to select. It is given at the centroid. If you look on here, if y1 is working at the centroid, it's not a centroid, it's actually a given point that is given here. So as I said, that Ansys cannot predetermine a centroid. So this point, when the geometry is created, this point is given into the geometry, okay, so that we can apply this boundary condition. So when this whole geometry being created, this point is being also created along with the geometry, and that's why we can now apply this Fy1 at the certain point. So for that, I have selected a force, and we have to use a point. That means, which one you have to use? You have to use the vertex, okay, this one. So if you hover your actually cursor here to see this point, okay, so it is predetermined when the geometry is created. Okay, so if you apply, and the positive y direction is here on this direction, so the force is also working on the positive y direction, and the value is 8,000. So if I give the value, it would be component, and the value in the y direction, it would be what? 8,000. Okay, okay, so now it's given. So now three forces have been determined in a boundary condition. So now one varying load is given. So this is a pressure type of force. So to determine that, we have to use the pressure. Okay, and which one you have to select? The phantom surface, because I said that Ansys cannot just determine the boundary condition on the geometry. You have to select a face or a point or an edge. So as it is working on the left, if you look on the geometry on the left, so we have defined a phantom surface on where we can determine this boundary condition. Okay, so for that we have to select this phantom surface, this one, and apply. Okay, and you go to the section, and the value is given as 0.1 times z psi. Yes, you just and make sure that the magnitude would be, and it is normal too, it will be as it is, and the magnitude would be, and make sure that you have the right unit. Okay, so it's given in psi. Okay, and it will be similar. You have to input this equation, which is 0.1 times z times psi. So you have to input an equation. It's similar to how you input the equation in Excel. You have to use an equal sign, and then 0.1 times z. It is in the z direction. Okay, so now if you apply, so Ansys automatically, you see, calculate all the forces, the varying load. Okay, so varying load. So if I rename that, it would be varying load. Okay, so now all the forces have been predetermined. So now one more thing I want to add, that is basically the weight of the actually the structure, whole structure. You see that I said that this is the weight of the sign and this is the weight of the post. So it is separately been applied. Okay, and also in our boundary condition we have separately applied the boundary conditions. But if we want to apply the whole force at once, that means this is the force, sorry, this is the weight of the sign and this is the weight of the force, and if you combine for the whole assembly, for the whole geometry, if you want to apply the force, okay, that will work at the centroid. Okay, there is an option for that in the Ansys. Okay, so if you do not have determine the actual weight separately, then you have an option in the Ansys to determine the force, that means the weight force of the whole geometry. For that you have to go to insert and you go to the standard earth gravity. Okay, see this one. So this is the centroid of the whole geometry, that is outside the geometry, and here the whole weight is working. But what we did, we have actually used a separate method. That means we have separately determined the weight of the sign and weight of the post. Okay, but if you do not have used that, then you could have determined the whole geometry weight at once by the standard earth gravity, but we're not using that, so we're going to delete that. Okay, okay, so now for the solution part. Okay, so for the solution you go to insert. There's different solutions for the deformation, the total, the strain. You can know the strain, you can know the stress, you can know the energy, and so on. So for the here I'm just gonna stick with the deformation, the total deformation, and the stress. Okay, the total equivalent stress. Okay, you can in the lab manual, when you make the assignment, you have to use the different sections as well. Okay, now if I use the solve, it's going to solve that. Okay, so if I apply solve, solving, see, it's been solved. So this is how it looks like, and we can see that the maximum force, sorry, the maximum, which is this one, the maximum stress, the maximum stress is working here, the red one. Okay, here. Okay, and the maximum deformation, if I zoom out, is working here. Okay, so to determine the minimum maximum point, you can have an option in Ansys. If you go to the result and go to the maximum and minimum, so you see this is the maximum point and this is the minimum point. Okay, and also we have a probe. That means if you hover the mouse, it's going to tell the stresses or the deformation at that particular point. Okay, so you can know the deformation or stress at a particular point. Okay, so you see, if I go into the stress, the maximum stress is working here. So I want to refine the mesh. I want to refine the mesh because I want to have a more exact solution onto just this portion. Okay, so for that you have to refine the mesh. Okay, so for that there are two options. Okay, so if you go to the sizing of the sign, sorry, signing of the post, so you can decrease the element size. That means the whole element size will be less, and as I said earlier, the less the element size, the better, the finer the mesh is. But it's going to give you a consequence. That means it will have a higher computational power. So but as from our solution we have seen that highest stress is occurring here. So I just want to refine this portion of the mesh. Okay, so for that you go here and right click, insert and refinement, and select this surface. Okay, and apply. Okay, and you want to refinement how many times? Okay, if you give one, that it means it will be as it is, and if you give two, that means twice the refinement, twice the mesh size it had before. And if you again increase it, that means thrice the mesh size it had before. So I'm gonna keep it as 3. And if I now generate the mesh or update the mesh, see, we have a more refined meshing here. If you look on here, sorry, if you look here, more refined meshing here. If you go to the properties of the mesh, we have much higher elements. Previously we had around 4,000, but now we have around 7,000 element size, and also the nodes number been increased. Now if you again give it a solve, okay, it's going to solve that, and we're going to have a more accurate result. And let's say the higher the mesh, the higher the better results are. Okay, so okay, so this all for the first Ansys experiment, the activity. Thank you everyone. Allah Hafiz.